All right. Second hour, although it's actually probably more like 50 minutes. So let's see where we're starting. It says 6:15 on this clock, and I do 50 minutes. I guess 5 minutes after 7 on that thing, which means nothing to you because you're watching on your own time. All right, so isotopes. They might give off something. They give off something that makes them change into something else. But that's only a radioactive isotope. So that begs the question, types of, this pen is out, types of radioactivity. Well, I mentioned one already, but you just didn't realize it. So let's talk about a particular isotope. Here's helium, 4, 2. So it's helium-4. A person could ask you, and they will ask you, who knows, write down the number of protons, neutrons, and electrons. Atomic number is 2. So there's 2 protons, 2 electrons, 2 neutrons. There are 2 protons in the nucleus. There are 2 neutrons in the nucleus. And then in the first shell, the first distance that has electrons in it, electrons are only going to be able to be at certain distances. It's the whole thing about the Planck's constant, that they only take certain distances or certain energies. The shell is an energy level. This would be the first shell, the first energy level. This has 2 electrons. So this is He, +2, -2, neutral. Helium stays neutral. You might be curious about that. Where can you find helium? Well, you can find helium on your periodic table. It's there. Good. Now, if I were to remove the entire shell of electrons, let's say I just could take them away. If I took not easy to do, but if I took the 2 electrons away, I would have nothing but the helium nucleus. 2 protons and 2 neutrons, but nothing to balance it. It wouldn't be neutral. -2, +2, it's neutral. It wouldn't be neutral anymore. It would be a +2. So this could be written as He +2. This is a charged species. It's called an ion, and it is not a popular ion. We don't make that species. Helium is neutral. In gas, it makes balloons float. But it is a charged species. Because it's a positive charge, it's called a cation. Giving you a glimpse of the future, there's going to be negative charged ones called anions, but for now, it's a strange cation. What is it? It is the helium nucleus. Now, an atom doesn't have to lose an electron to become a nucleus, and it hardly ever does. It hardly ever loses all of its electrons. Only one of them does, really. But we'll talk about him. It's not him. But if you could, you'd make helium +2. That is the helium nucleus. If you had a block of a radioactive isotope, trillions and trillions and trillions of this atom, a block of a radioactive isotope. That's my bicep pen. Yeah. And you had your wand, and you were collecting on your Geiger counter, and you heard something hitting it and it went click. Something could be coming off of it. Well, believe it or not, if there's the thing, if a helium nucleus is ejected from, there's a good pen actually, a radioactive isotope, we call this an alpha, ALPHA particle. So, types of radioactivity. Radioactivity sounds like a click when it hits the wand of a Geiger Mueller tube. But different things might be coming off. And one of the three things that we'll talk about that does come off is, believe it or not, from larger atoms, they can eject little packets of 2 protons and 2 neutrons. They're very big, speaking wise. So, type 1, alpha, ALPHA particles. It's a packet of 2 protons and 2 neutrons ejected from an atom. Get my pen and my paper, and I'll get this thing that I'll call my wand. Let's say this eraser here, you can see the eraser, yes. Let's say this eraser here was radioactive and it was an alpha emitter. My wand could go over it and go click, 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 and it's a very hot alpha emitter. It gives a lot of them. Or it can go click, 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 and it's a very cold alpha emitter. It's barely giving any of them. But if I go like this and it goes click, 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 a piece of paper makes it stop. These are so big that paper can stop it. And paper is nothing but glucose. You'll hear about that, okay? So, it's a long story. So, to make a long story short, hopefully, paper can stop it. So, it has a strange set of properties. The alpha particles, which is a packet of 2 protons and 2 neutrons, alpha particles are safe outside you. Paper can stop them. So my skin can stop them. I'm not going to get hurt. The alpha particle hits my skin, big deal. It's bounced right off. But these are most dangerous if you eat them. They can be stopped by paper, they can be stopped by skin, but if I eat them, they can't get out of me. So they bounce around and just disrupt things. So internally, called ionizing radiation. Can't spell that. You didn't hear the word though. You just hope someone doesn't poison you. If somebody gives you something, it wouldn't taste like anything different, but God forbid it had alpha particle emitters inside of it, and inside your stomach they couldn't get out and just did incredible damage, okay? So there's probably some countries who use it to hurt people. We just don't know who. I could do politics. Second type of particle. This is strange. It's called a beta particle. VETA particle. That's the symbol. That's an alpha particle, that's the symbol. Okay, if you're wondering. A beta particle is an electron emitted from the nucleus. It's an electron that's emitted from the nucleus. And that shouldn't be the most comfortable thing to you. Because what's inside of the nucleus? Protons and neutrons. Electrons are in shells outside of the nucleus. So how could an electron be emitted from the nucleus? Because what's inside the nucleus? just protons and just neutrons. But it's still true. When a beta particle, let's say this was a beta emitter, it's an unstable radioactive isotope that gives off beta particles, electrons emitted from the nucleus. This is my wand. I put this here with paper and it keeps clicking. The paper can't stop it. Aluminum, pretty thick aluminum foil can actually stop it, if you're curious. I do an experiment with that, but you guys will probably not have live experiments, but I often have like radioactivity in the labs. So that's just a lot of fun. So here's your beta particle emitter. It can be stopped by pretty heavy aluminum, so can be stopped by aluminum foil. Now I want to make a point here. It can be stopped by aluminum foil, but it can't be stopped by paper. So it can definitely be stopped by lead. The alpha particle can be stopped by paper, so it can definitely be stopped by aluminum foil. I hate for you to think that aluminum foil is the only thing that can stop something. Aluminum foil or anything thicker, paper or anything thicker, let's leave it at that. So how is it emitted from the nucleus? Well, what's in the nucleus? Protons and neutrons. Neutrons and protons weigh the same. I said that electrons, 1,836 electrons weighs the same as one proton or one neutron. So if you have a neutron in the nucleus minding its own business, and it gives off, believe it or not, an electron. How in the world it gives off an electron is a long story. It would be the same weight, but no longer neutral. What is the same weight, but no longer neutral? Well, it's given off its negativeness, so it must be getting positive. If it gets positive, believe it or not, neutrons becoming protons give off beta particles. So that's a beta particle, an electron truly from the nucleus. It's not coming from one of the shells. So neutrons can become electrons, if you're wondering. You often hear about atomic bombs, etc. If you have the weight of all the things that you put in the atomic bomb, all the uranium or plutonium, etc., and you weigh all the daughter particles, there's a little less weight than what you put in originally, but a ton of pure photonic energy that takes a whole city out. So when you split the atom and you make a nuclear bomb happen, a nuclear explosion, somehow protons and neutrons are becoming pure photons of energy. So if that can happen, you can assume that neutron can probably become a proton. Why not? I'll talk about something else. Not one of the three big types of radioactivity. But if you had a proton and it became a neutron, instead of a neutron becoming a proton, going from neutral to positive, if you have something positive becoming a neutron, it would be the same weight because the neutron and proton weigh the same. But it would be missing its it would be missing its positiveness. Somehow, if a proton could give off a positive electron, let's say. If a neutron, which is neutral, gives off an electron, it becomes a proton. If a proton gives off a positive electron, it becomes a neutron. So what's a positive electron? Something we hardly ever talk about. It's an electron with a positive charge. That's called a positron. I don't know, Star Trek had a character, a robot, that a sentient being that had a positronic brain. But, you know, if you've had a PET scan, that thing is something that can give off positrons. It's a device that can give off positrons and use it to like look at stuff. So we can make positrons, all right? But it's not one of the three big radioactive particles. In nature, some isotopes are stable and most are stable, but some are unstable. They either give off the alpha particle or they give off the beta particle, or believe it or not, The third type, see, this type is not that exciting for nature, but it's interesting because it's a positive electron. But the third type would be a photon is ejected. And it's such a hot, because remember, I gave you the electromagnetic radiation scale, the highest of all the types of photons. The lowest was your cell phone battery. Your cell phone call. Your cell phone call is traveling at the speed of light. Visible light is traveling at the speed of light, but it's higher energy. The highest was gamma. Believe it or not, some radioactive isotopes can give off a gamma particle. Now these can only be stopped by lead. And I'm talking thick lead. I've had the students have some radioactive isotope and have a piece of lead on top of it, and this guy, this wand from the Geiger counter is reading click, 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 and if you put it over this particular gamma emitter, it goes click, 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 click. You put the lead on top and it goes click, 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 still a little bit faster. Some actually get through. So it's pretty amazing. So it's actually quite dangerous, but not if you eat it as much, because if you eat it, it flies right out of you, because it's only a light photon. It's kind of interesting. So this guy is safest outside of you, most dangerous inside of you, and that guy would be probably the least dangerous inside of you, because you couldn't hold it. It's going to fly away at the speed of light. All right, so let's erase this. What can you do with radioactivity anyway? Well, no one's here to answer that question, so I guess I'll write it. I'm in a room talking to myself right now, but this is the new world. Hopefully someone's going to listen. I got to figure a way to make sure you watch these things, and sure I will. All right, uses of radioactivity. First of all, power. If you start a radioactive reaction happening, but you don't take it all the way to the nuclear bomb, you can actually heat a lot of water with it and things like that. So nuclear power is pretty amazing stuff. It's actually extremely clean. If you drive by a nuclear power plant, it looks like this very strange device. It's like 3 of these things, and they're giving off this smoke, but it's just steam. They're not really dangerous, okay? We could have really done well with nuclear power. We use fossil fuels right now, okay? That's going to be a discussion I get into probably pretty soon, okay? But we use fossil fuels right now, or we use solar power, or we use wind power. And the sun doesn't always shine and the wind doesn't always blow, so you have to have backup energy, so we use natural gas, which is a fossil fuel. But these things give really clean power. Sadly, if they're not controlled and they melt down, they give off radioactivity and they're dangerous. So there was a famous thing in Russia called Chernobyl, and like America, no matter how much debt we have and how much we've messed up our economy, America is sitting on top of a lot of raw material. So worst comes to worst, we could always burn coal. Well, places like Japan don't have any raw material underneath them that they can burn. So poor little Japan, that had so much nuclear power. France, the same way, it had a lot of nuclear power. In the 1970s, we had the thing called 3 Mile Island incident, where it scared us so much we stopped building nuclear power plants. Which is kind of a shame, because if we kept them safe, they would have been a really great source of clean energy as long as you keep them safe. Japan, well, that didn't worry them at all, because they don't have any other power under the ground that they can harness, so they used nuclear power. They did quite well with it. And they had this one plant too close to the shore. And they said, the Fukushima plant will be fine, we're not going to worry about, as long as there's not a tsunami and an earthquake at the same time, we'll be fine. Well, a tsunami and earthquake came, and some really strange things happened, and they made a very radioactive area for themselves. So anyway, you can use it for power. What else can you use it for? Well, of course, nuclear weapons. You think of the atomic bomb. But let's say you have some spent fuel from a nuclear power plant that's still quite radioactive. If you mix it up with, I don't know, gunpowder and put it in something that explodes. Now I gotta tell you what explosions are, okay? But if you mix it up with something and just puts radioactivity all over somebody, that's what we're worried about a lot of times, calls a dirty bomb. Okay, you don't have to have a whole nuclear bomb to have like nuclear particles or radioactive isotopes that can hurt people fly around. But while I'm at it, let's explain the word explosion. A gas forming process in a closed container. A gas-forming process in a closed container. Gasoline burns. Gasoline is flammable. If I pour gasoline on the floor and light a match, I see it, light. But that's not an explosion. It forms carbon dioxide and it forms water, which is a gas. But it's not in a closed container. If I take gasoline and put it inside of a jar, a glass jar, and then I put a rag in it and I throw it, which is a horrible, horrible thing to do, the gas forms so quickly, it shoots out shards of glass. That's an explosion, if you're wondering what an explosion is. So a lot of times students are like, is it gonna blow up? It's gonna blow up. Very few things blow up. We don't set up chemistry that it's gonna blow up all around the place, okay? If we have a beaker, the top is not on it usually when we're heating it. So anyway, get past that. Uses of radioactivity. We have the power plant, we have the nuclear weapons, and then I'm going to use this word carefully, medicine. And this is going to pick up in the drug chapter, but either way, medicine. How do we use it in medicine? All right, let's see. Well, since it's a class, and I know we're going to get to it later, you can get sick from bacteria. But we need bacteria to break things down. You could get some sort of a strep infection. There's a long story about that. It can reproduce itself. It's a real living cell. This, you take antibiotics. Then you can get sick from a virus. And now that thing is just like a computer virus. It needs something to replicate it, so it uses your own body to replicate it. Some viruses you can pull out with a vaccine because they have a protein shell that doesn't change. Some, the protein shell changes so much the vaccines don't really work. So the common cold. Luckily, it doesn't kill us because we really can't make a vaccine to it because it shifts too often. Okay? You could make a vaccine to the common cold, but you have to keep giving to people the thing every so often. COVID is one of those viruses that probably is going to mutate a lot. But anyway, that is what it is. HIV is one of those viruses that mutates a lot. But HIV, you cough this far and it's not able to be viable. Okay? So how long can it live on a surface? Hepatitis? If you cough on a table and then a week later it's still, that kind of thing. So the viruses have different levels of stuff. But back to how you can get sick. You can get sick for many reasons. But you get sick from bacteria, you can get sick from a virus, or you can get cancer, which is human cells that grow too fast and cause problems. They're interesting. I mean, you get these things called tumors, and a lot of times the tumor can be really jealous. The tumor is eating. Okay, the tumor is a bunch of human cells that are growing too fast, like my hair. Okay, your hair grows too fast. So getting past that, it's true, hair grows faster than regular cells, human cells. So if you have human cells that grow too fast, they can cause a tumor, and the tumor may not do that much damage to you. It might be doing damage, but either way, it sends out a signal unique to you to all your whole body's saying, I don't want any other tumors to grow, I want the blood. I gotta be fed blood. So a lot of times if you go in for cancer, cancer is going to seem very barbaric later in your lives, like in 100 years. But for now, what do? We pull the cancer out of you. We chop it out of you, okay? And then we don't know why you grew the cancer in the first place. If it's one of those cancers that's for a particular reason, you're in better shape because then just don't go near that reason again, okay? Like there's some estrogen positive cancers, etc. And you just don't take the estrogen replacement therapy, that kind of stuff. You have something you could do. But if a person is naturally getting cancer, like every day in your life, you get cancer and you cure the cancer. You just don't know it. It's in my opinion, but it's probably true. So anyway, you've got this tumor inside of you. You could cut it out, but then there's other issues. Maybe half a year later, you're going to have a situation where it's spread and metastasized through the entire body because all the other cancer cells can now grow anywhere because the master tumor is gone. It's like a shared relationship. You got to figure out what's better to do, and it's all different for these things. Now, ways we treat cancer. And my lecture's making sense. I'm not going off on tangents or anything like that. Well, what do you got to kill? You got to kill human cells that grow too fast. So, to treat, we give poisons to human cells that grow too fast. And that's a chemical therapy. That's chemotherapy. So they might take the tumor out of you and then say, to make sure that the lining around where we took the tumor is not going to regrow a new tumor or cause any trouble, we're going to give you certain chemicals that target cells that grow too fast. Now your hair grows too fast, so when you're in chemotherapy, your hair falls out, okay? So it's gotta be pretty rough stuff. But we're trying to kill human cells, and the rest of your other cells are like, well, I don't like the poison that much either, okay? So it's a really rough thing. Then, I really want students who come out of this class to have like a basic set of knowledge about how to like live their lives if they're not scientists. Chemotherapy is not radiation therapy. Then there's radiation therapy. And that is medicine. Okay? That is medicine, if you're curious. Radiation therapy is some type of a medicine. How is it some type of a medicine? Well, it's dangerous. So if I have an inoperable tumor next to my heart that I can't get rid of, because if I operate, my heart's gonna not be able to handle it. They can take a radioactive isotope that's extremely dangerous in a pill form, but not swallow the pill, right? Take it, open up next to my tumor, put this little pill next to it, close it, and then open up a week later and take it out. They're hoping that it irradiates the heck out of that little tumor and kills it. So it's actually quite a dangerous thing to do. Like if you have prostate cancer, men never even knew about prostate cancer. As men, we used to, we died of heart attacks in our 60s a lot of times. And then blood thinning drugs came and everybody said, oh my God, we're gonna live so much longer. Well, when we lived longer into our 70s, blood pressure pills and blood thinning drugs, we suddenly realized there were other things that would kill us, and prostate cancer is one of them. So if you get prostate cancer, they could do radiation therapy. And what they do is they put your body in like a mold, and they say, we're going to put a beam of focused radiation directly at that tumor. Okay, what's a beam of focused radiation? Let's say I got a lead box. And I have an extremely dangerous radioactive particle inside the box. It's going to irradiate in all directions. And by the way, you don't have to like put any power into this thing. It's got a half-life. It lasts a long time. Okay, it's going to radiate in all directions. If you put a hole in the box, then the radioactive particles that are coming off are going to hit all these walls and do nothing, but they come out. Oh my God, we got a beam. Okay? It's some primitive stuff. So people like radiation therapy because it doesn't have the side effects of chemotherapy, but I swear to God, you gotta be careful with all these things. A lot of times when people get radiation therapy on their skulls, there's some issues later with their brains. So, I mean, just try to live a good life and be healthy. So these are the uses of radioactivity. I've explained radioactivity. Now I'm going to continue teaching. Erasing the board. Oh, I can erase this and not ask you if you've seen it because you can stop the camera and just write the notes yourself. And a lot of you are like, well, I'm never going to write those notes. That's fine. But if you came to get a liberal arts degree and you wanted to be well-rounded, you should be so lucky to have somebody try to teach you this. You came here and you said, you know, if you're a nursing student, let's say, you came here and you could have went to Galen and just learned about nature, but you said, no, I want to go somewhere and learn about religion. I want to learn theology. You come to a place like this because you're intellectually curious about all kinds of stuff. And that's what the liberal arts schools are good for. That's probably one of the many things we're good for. How about that? All right, so with that in mind, let's talk about our periodic table. I'm going to draw on this board. You, since you have printed out your periodic table, you could probably just write all over it and then make many, many copies of that periodic table. So, well, here we go. Let's see if I can even pull this off. It's not going to be beautiful, but it is what it is. All right, well, there we go. All right, I'm not going to draw all the atoms in this thing, right? So let's go here, here, here. And this is hydrogen, it's got a 1, lithium, it's got a 3, beryllium, it's got a 4, sodium, magnesium, this one's got an 11, this one's got a 12. Below sodium, there's potassium and calcium, and this is a 19. And I'm only doing the atomic numbers now. I don't care about neutrons anymore. And this is 20. Now, there's a bunch of atoms in the center here we'll speak about. I need 6, so I need 5 lines. 1, 2, 3, 4, 5. 2 of these, 2 of these. Here's helium, it's 2. Boron, carbon, nitrogen, oxygen, fluorine, neon. Draw a line here. And then we'll have aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And then we'll say 5, 6, 7, 8, 9, 10. And over here we'll say 13, 14, 15, 16, 17, 18. And maybe I'll go down here and I'll put krypton. I could use that now. And I'll put beryllium, boron, bromine, goodness, boron, bromine here, and let's make that 35. So this would be 36. Okay, a periodic table. Truly amazing, right? This thing was set up by Mendeleev, and people were like, oh yeah, that's a cocky thing to do. You got to take every single atom and put them in order and tell me stuff about them. And he said, yeah, it's going to be amazing. Until then, we just had an agglomeration of atoms, and we had these weird things called triads, where we had like atom, 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 kind of do stuff like each other, atom, 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 kind of do stuff like each other. This group kind of does stuff like this, so we put the triangle next to it, and it was really strange. This guy, this Russian chemist, or Russian, I guess chemist, went out of his way to say the whole thing fits into order, and people didn't believe him. And he said, okay, well, chemicals have certain properties, and these columns are groups, and these groups act the same way. So I'm going to guess about this guy right here, which doesn't exist. Something below silicon. He called it eco-silicon. And he said it's going to form this, it's going to have this density, it's going to do this, it's going to follow. And they were like, oh my God, you don't know what you're talking about. But when they found what is now called germanium, gosh darn it, it had all those properties. And they were like, wow. So they were like, oh my God, we discovered something from God. This entire thing was planned this way somehow. So it's pretty amazing, and he was very cool for doing that. Now, these are rows going across. We'll call them periods. the first period, the second period. The second period is going to be lithium, beryllium, boron, carbon, nitrogen, oxygen, all the way to neon. So going across, there's some periodicity that we're going to deal with. Looking at your periodic table, which I Xeroxed back in 1991 when I was teaching this. This is from, well, I probably should Xerox something else. I Xeroxed it from this Navy thing. I can't tell you how many students come up to me and they say, the weirdest thing, do you support the Navy, Dr. Sinski? And I'm like, well, I don't hate the Navy, but it's because my periodic table has the word Navy. It's because I went to a Xerox machine in 1991 and did that, if you're wondering. So, anyway, here's aluminum. You'll see a bit of a line here. Xerox for the 50th time. It's hardly visible anymore, but it's a stairwell. Now, hydrogen. Let's speak of hydrogen right away. Here's hydrogen. Atomic number 1, atomic weight 1. On your periodic table, you're going to see 1.0079. If we have 1.0079, there could be a hydrogen 2, but there can't be that many of them. Because if there was as many of the isotope hydrogen 2 and hydrogen 1, you would have an atomic weight of 1.5 on there, but it's 1.0079. This is the natural formula. As I showed you already, to get the number of protons, neutrons, and electrons, 1, that defines it, so it's got 1 proton. 1, that defines it, so it's got 1 electron. It can lose that electron or share that electron, but it can't change to 1 proton. Then, the atomic weight is the number of protons plus the number of neutrons. 1 minus 1 is 0. This thing doesn't have any neutrons. A hydrogen atom is nothing but a proton and an electron floating around together. It's a very strange species. It definitely can't make a metal sword. That's going to become a thing, okay? Now this guy, he's got a proton. He's got a neutron because 2 minus 1 is 1, so he's got a neutron. This is heavy, so if you make water with this species here is called deuterium. So sometimes they put a D instead of this species. Hydrogen 2 is deuterium. This is H2O. You can get a beaker of D2O, and it's actually quite heavy. And it's like, wow, that's kind of interesting. It's heavy. So, long story, heavy water, used in nuclear chemistry, don't need to go there. But what I do need to say to you is that hydrogen definitely can't make a sword, okay? Back to this stairwell. Everything on this side of the stairwell, except for hydrogen, is a metal. And everything on this side of the stairwell is a non-metal. Let me do it down here. So a non-metal. There you go, a metal and a non-metal. Now, that was how we did in the old days. These days they say, well, these kind of behave a little bit like both, so along the stairwell they do call them metalloids, all right? And they can do strange things like Silicon Valley. You're going to have these things that they do with electrons. But anyway, for me, metals, non-metals, these are periods. You will use this in your life. You're going to have a student going through school as a child someday. You're going to be like, look, Dad knows this. Whatever you want to do, you want to say, Mom doesn't know math, Dad doesn't know math, because then they think it's bad, and they're like, well, then I don't want to know math. And you could be rich in this world as a lawyer without math. Everything else needs some math, okay? So we can't all be lawyers. They're all of our politicians. Now, our columns, 1A, 2A. In America and in Russia, we jump to here and call this 3A. So this is 3A, 4A, 5A, 6A, 7A, 8A. And these are our B's. In Europe, they go right across the entire thing and they have like the number 16 up there and stuff. And sometimes they call these A up to here and B over here. This group in the center is a metal, but it's going to change something. We'll talk about it. This group, and not all of them, okay? In the first year of chemistry, we don't tell you all the anomalies because then you wouldn't love studying, okay? But this stuff in the middle, these are the transition metals. if you're curious, these are the transition metals. We'll talk about them. Iron was smack dab in the middle of that thing. So anyway, some of these columns matter to us. Like when I do the lawn chemistry stuff, it's going to matter. When I do the farming chemistry stuff, it's going to matter. The 1A column, hydrogen is not a metal, okay? Sometimes you see hydrogen written over here. Sometimes you see helium written over here, depending on what we're trying to emphasize with you. But the 1A element is not, I'm sorry, the hydrogen is not a metal, but the rest of them are metals. The 1A are called AlKali, alkali metals. Now, when I taught this class for many years, I'd have people memorize certain things, but you know, it's impossible if you're online, and what I ended up doing is making the in-person people have the same type of exams on the weekend because I want to make this fair. I don't want them to have to memorize a bunch, and you don't have to memorize things, okay? So, alkali metals. The 2A are the AlKali, earth metals. These are language things we need to understand chemistry. A soil can be very acidic or it can be very basic. If it's basic, it's often called alkaline because it has something to do with these metals, which we'll talk about. Okay, so I'll talk about acids and bases pretty quickly. But getting past that, the 2A are the alkaline earth metals. So calcium, beryllium, magnesium, etc. And then the 1A are the alkaline metals, lithium, potassium, sodium, rubidium, cesium, things like that. The 3A have a name, don't need it right now. The 4A have a name, the 5A have a name, the 6A, chalcogens, but I don't need that. I need the 7A, okay? The 7A, 5, 6, 7, these are the halogens. And I'm going to say this, and it's going to make sense soon, as salts, or I hope it does, you call them halides. But they're the halogens. These are words you've heard of. Alkaline battery, it probably has one of these particular atoms in it from this second column. Halogen, you could have a halogen headlight. For the longest time, when halogen headlights first came out, they give a different spectrum of visible light off. And when you saw them coming at you at first, they didn't look like incandescent yellow lights in the 1980s and stuff, and it really freaked people out. They were like, what's wrong with that car? It's coming at me in a very, because you don't like that. You don't want someone shining a black light at you. Well, these things, luckily they didn't catch on that well, but for the longest time, they're really not that bright. Here's a good example. I got here in 1997. I drive a 1997 Ford Taurus, right? It's got 250,000 miles on it, and I'll probably die in that car or something someday, or it'll be buried with me. But this 1997 Taurus, it has headlights, and my wife always says, oh my God, these lights are so dim. I have turned the lights on bright, and I have replaced these headlights. And I drive around with those lights on bright, and they're still dimmer than every other car's headlights. It used to be we had a much dimmer world, but now you guys have the brighter and brighter lights, so no one ever flashes at me and says bright, okay? Because my bright lights look the same as the average light these days. It's not even as bright. Pretty amazing. But anyway, there must be something to do with halogen atoms. Now, the 8A, everyone needs the 8A. 5, 6, 7, 8, let me write over here. They're important. Yeah. The 5, 6, 7, 8A, these are the noble gases. They used to be called the inert gases because they did not react with anything. Well, as chemists, we forced them to react. We forced krypton to take a bunch of fluorines it didn't want to. So can you really call them inert anymore? Now they're the noble gases, all right? And you've probably heard this in your life, but let's teach it as if you haven't. Atoms, I hate this expression, want as many electrons as a noble gas. They can give away take or share electrons. Keep writing. In bonds. They can give away, take, or share electrons. There's going to be types of bonds pretty soon. The atoms are trying to get like a board game to the noble gas. And by the way, chlorine is Cl. Fluorine is F. Students write FL because they feel bad for fluorine because he doesn't have an L because chlorine has one, or I don't know why. But I stopped taking points off for that. F though, just F by itself. All right, let's continue on here with these atoms. There's another set of atoms I haven't shown you yet. But first, there are some reactive metals. Sodium. If I show you sodium, it has an atomic number of 11. So it's got 11 protons and 11 electrons. It's neutral. In my opinion, I don't think there was ever any sodium on this planet that was neutral until we came along and forced it to be. It hates that configuration. It has 11 electrons. It wants to have as many as a noble gas. They all do. It can pick up 7. 11 plus 7 would give it argon's configuration of electrons. It's still going to have 11 protons. That's not going to change. But it can pick up 7 and have as many as argon. That would be fine. But it could also, remember, it's got 11 protons. It's not going to change. It could lose 1 electron, go from 11 down to 10, and that's the easier way to do it. It becomes neon's electron configuration. It doesn't become neon. So sodium, once neon's electronic configuration, loses 1 electron, and it becomes Na plus 1, a cation. The sodium atom is not noble. Neon is noble. Neon light doesn't have to react. Helium is noble. Argon is noble. The sodium atom is not noble. If you take pure sodium atoms that we've created that are neutral and you put them underwater, they catch on fire. They will throw their electrons at anything. This metal is not neutral, but there are some metals that do occur in nature that are neutral. A few. I have a gold ring, okay? This is a wedding ring. When you get married, you put one of these things in your hand. I usually put it on this hand. It's a long story. I've got another one on the other hand. That's a 2,000-year-old just piece of junk. But getting past that, gold, AU, silver, AG. Those can exist uncharged. You can find them in nature uncharged. Gold is a noble metal, silver is a noble metal, but the other metals aren't. Iron, you're not going to find iron neutral. You're going to find iron in rock. Most of your atoms are locked up in rock. The one metal that we recycle is because it costs money to make it neutral, aluminum. The most abundant metal on this planet is aluminum. It's all that Kentucky red clay, okay? So we have a ton of aluminum metal on this planet. But to make it go from Kentucky red clay to aluminum foil is pretty expensive, so we recycle it. But iron is pretty cheap. You just heat the rock up with some carbon and you get it. We'll talk about that. Stone Age and all that kind of stuff becoming the Bronze Age. Long story. But since iron can easily be heated up, we bury cars, we bury refrigerators, we got way less iron. It's the strangest thing. The metal we have the most of, we're so worried about the most. Okay, so getting past that, there's one more set of atoms on this periodic table I have not shown you, and I'm going to show them real quickly in this next minute because I'm going to keep to my word. Bunch of atoms down here in the bottom, 14 different boxes here. These are the rare earth elements. Hardly need to talk about them, but what's interesting about them? Well, let's see, you've got uranium, you've got plutonium, they're really big, they're easy to split, okay? So these things here should be up here. If you look on your periodic table, I'm assuming you are, scandium, titanium, 21, 22. Yttrium, zirconium, 39, 40. Lanthanum, hafnium, 57, 72. Something's missing here. These stick right here. So the periodic table should look more like this. You got that, then you got that, then you got this long set of these rare earth elements, and it goes up, then it goes way over, then it goes up, then it goes way over, and it looks like this. This is what the periodic table should really look like. But, you know, the font would suck, okay? So you wouldn't be able to read it unless we all had legal paper, all right? So I think the scientists a long time ago said, take these, drop them to the bottom, and shrink it together. That's what it is. So that's enough for your first week of lecture. Always look at emails every single night. I do write you quite often. I'll write you more often, I promise. I know you're probably getting lonely. So anyway, that's it. I'll be putting this up, but by the time I do, you'll know it's up, won't you? Okay, so I'm going to stop recording. I hope it's what you students expected for your first day of lecture.